On the 6th of March, 1944, at an altitude of 28,000 feet above Berlin, the 56th Fighter Group clashed with German aviators in an aerial confrontation that would become the most extensive witnessed over Europe to date. Throughout the sprawling engagement, pilots of the American Thunderbolt discovered something that profoundly startled their Luftwaffe adversaries. German fighters employed their customary escape tactic, initiating steep climbs to break away from pursuit. For the preceding year, this maneuver had been virtually foolproof. The heavy P-47 Thunderbolt was simply incapable of keeping pace with a climbing Focke-Wulf 190 or Messerschmitt 109. However, on this particular March day, a fundamental change had occurred. American fighters maintained their lock on German tails through climbs that should have been impossible. At altitudes nearing 28,000 feet, with both aircraft operating close to their stall speeds, the Thunderbolt pilots opened fire. Dark plumes of smoke trailed from stricken German aircraft as their pilots parachuted to safety. By the conclusion of the mission, the 56th Fighter Group reported the destruction of 11 German planes, without the loss of a single Thunderbolt. The transformation was now complete. An enhancement to the Thunderbolt's propeller had eradicated the aircraft's most critical vulnerability and fundamentally shifted the tactical balance in the skies over Europe. The genesis of this significant development can be traced back to the engineering departments of two American propeller manufacturers during the harsh winter of 1943. While bomber formations bled casualties over Germany and fighter pilots submitted reports detailing German aircraft escaping by climbing away, engineers diligently worked to resolve a deceptively straightforward challenge. The Pratt & Whitney R2800 engine delivered an impressive 2,000 horsepower, yet the P-47 Thunderbolt exhibited poor climbing performance. The narrow-bladed Curtiss electric propeller fitted to early production models was unable to translate that immense power into effective vertical ascent. These blades were engineered for optimal performance during high-speed cruising. They were fine-tuned for slicing through the air with minimal drag at speeds exceeding 350 miles per hour. During climbs at lower airspeeds, with the engine operating at maximum output, these narrow blades lacked sufficient surface area to effectively convert horsepower into forward thrust. Engines roared at their maximum revolutions per minute, consuming fuel and generating heat, but failing to propel the aircraft upward with adequate force. In January of 1943, at the headquarters of Republic Aviation Corporation in Farmingdale, Long Island, Alexander Cartelli reviewed combat dispatches from England with deepening apprehension. German fighters were diving through bomber formations, executing attacks, and then pulling into steep climbs to escape. Pursuing Thunderbolts were unable to follow. The performance data was damning. Early P-47 models required protracted climbs to reach operational altitudes. The Focke-Wulf 190A and Messerschmitt 109G reached these heights considerably faster. This performance disparity directly translated into American casualties. Pilots perished in situations where superior climbing performance might have preserved their lives. Some commanders within the Army Air Forces began to question whether the P-47 should continue in frontline service. Cartelli grasped the core engineering problem. Propeller efficiency is intrinsically linked to matching blade area with operational conditions. Narrow-bladed propellers functioned optimally at high speeds where their slender profiles minimized aerodynamic drag. At lower speeds during climbs, blades require a greater surface area to engage the air and effectively convert engine power into propulsive force. Increasing blade area seemed an obvious solution, but proved complex in practice. Any alteration to the propeller design had cascading effects on the entire aircraft system. Incorrect blade geometries could induce vibrations capable of tearing engines from their mounts. Improper weight distribution could generate resonant frequencies, leading to catastrophic structural failure. Inaccurate torque characteristics could render aircraft uncontrollable during takeoff. Republic Aviation urgently needed propellers with significantly expanded blade area that could be integrated into existing airframes without extensive modifications. Two companies vied to address this critical need. Curtiss-Wright, the manufacturer of the original narrow-bladed propeller, and Hamilton Standard, a supplier of propellers for numerous military aircraft. Both firms recognized that the victorious design would be produced in quantities exceeding 10,000 units. More importantly, it would directly influence the survival rates of thousands of American pilots. Engineers at both organizations labored through the winter of 1943, meticulously testing various blade profiles in wind tunnels, calculating stress loads, and constructing prototype hubs and pitch control mechanisms. American pilots were falling while engineers refined blade chord lengths and twist angles. Hamilton Standard's engineering team conceived a radical departure from conventional propeller design. Instead of thin, knife-like blades that sliced through the air, they proposed broad, paddle-shaped blades designed to grip the air like oars pushing through water. The blade chord would increase dramatically. The blade shape would be almost rectangular for a substantial portion of its length, tapering only near the tip. This design appeared rudimentary to engineers trained in traditional aerodynamics, but wind tunnel tests yielded remarkable outcomes. The design generated significantly more thrust at lower air speeds while incurring only a minimal reduction in top-end performance. Curtiss-Wright responded with their own wide-bladed design, retaining a more conventional elliptical blade contour, but dramatically increasing the overall surface area. The Curtiss design incorporated blade cuffs at the root to streamline airflow into the propeller hub and mitigate vibration. Both proposed designs represented substantial advancements over the original narrow blades. Republic Aviation received prototype propellers from both manufacturers in April of 1943. Testing commenced immediately at Republic's facility and at Wright Field in Ohio. Republic's test pilots systematically evaluated both configurations. The evaluations revealed that both the Hamilton Standard and Curtiss propellers delivered nearly identical performance enhancements. Climb rates improved dramatically with either design. Hamilton Standard offered slightly smoother operation owing to its hydraulic pitch control system. The Curtiss design integrated more readily with existing aircraft systems and would be easier to retrofit onto P-47s already deployed overseas. Neither option was definitively superior across all performance metrics. The Army made a pragmatic decision driven by manufacturing capacity. Both designs would receive approval for production. Hamilton Standard propellers would be installed on new P-47s manufactured at Republic's Farmingdale facility, commencing with the P-47D-22 model. Curtiss paddle-bladed propellers would be fitted to P-47s produced at the Evansville, Indiana, factory, and would also be supplied as retrofit kits for earlier aircraft operating in England. This decision prioritized rapid deployment over protracted evaluation to ascertain theoretical supremacy. The dual-source strategy would also complicate German intelligence efforts. Production commenced in June of 1943, but manufacturing and testing delays meant that the first operational aircraft did not reach England until late December of 1943. Throughout December, P-47s were flown to RAF Wethersfield, where mechanics retrofitted them with the new propellers. The 56th Fighter Group, based at Boxted in Essex, completed its transition by early January of 1944. Group Commander Lieutenant Colonel Hubert Zemke immediately recognized the tactical implications. The dramatically improved climbing performance meant his pilots could engage German fighters using vertical tactics that had previously been suicidal with narrow-bladed propellers. Zemke organized intensive training throughout January of 1944, developing new combat procedures specifically tailored to the paddle-bladed Thunderbolt's enhanced climbing capabilities. He instructed pilots to engage German fighters in climbing spirals, maneuvers that would previously have left them exposed. He devised techniques where pursuing P-47s would sharply pull up if enemy fighters attempted to climb away, converting speed into altitude and then dive back onto their targets with accumulated energy. With narrow-bladed props, these maneuvers would have left Thunderbolts wallowing at low speeds. With paddle blades, they became devastating offensive tactics. January 4, 1944, marked a significant milestone. The entire 56th Fighter Group flew its inaugural mission with all aircraft equipped with paddle-bladed propellers. Pilots immediately perceived the difference. The aircraft climbed with an eagerness that seemed improbable for 7-ton fighters. Energy retention during vertical maneuvers improved dramatically. Thunderbolts could now follow German fighters into climbing escape maneuvers without losing ground. The true test would materialize when they encountered the Luftwaffe over Germany. Their combat debut occurred during escort missions in late January and early February of 1944. American fighters found themselves in situations where German pilots employed standard escape tactics, only to discover pursuing Thunderbolts matching their climbs. Initially, German pilots assumed they were confronting a new type of American fighter. When intelligence officers analyzed gun camera footage clearly depicting standard P-47 Thunderbolts achieving this performance, confusion rippled through Luftwaffe units. How could the same aircraft they had successfully evaded for months suddenly match their climbing performance? March 6, 1944, provided dramatic confirmation. Lieutenant Colonel Zemke led 48 Thunderbolts on a bomber escort mission to Brunswick, routing over Berlin. Luftwaffe controllers scrambled more than 80 Messerschmitt 109s and Focke-Wulf 190s toward the incoming bombers. As the bombers approached at 24,000 feet, German fighters attacked using their standard tactics, diving through the formations and then pulling into steep climbs to escape their escorts. Across the battlefield, Thunderbolt pilots engaged German fighters in vertical combat for the first time. Captain Robert Johnson, Lieutenant Walker Mahurin, and other pilots of the 56th Fighter Group intercepted German fighters during climbing engagements and destroyed them at high altitudes. The group claimed 11 aerial victories without sustaining the loss of a single Thunderbolt. More significantly, not a single bomber in their escort formation was shot down. German pilots landing after the Brunswick mission reported disturbing developments. American Thunderbolts were ascending with them. Multiple pilots insisted they must have encountered an entirely new type of fighter. When presented with gun camera footage showing standard P-47s achieving the reported performance, their confusion intensified. Luftwaffe technical intelligence urgently needed to comprehend what had changed. The first clue emerged from wreckage analysis in early February. A downed P-47D-23 was transported to the Luftwaffe test facility at Rechlin. Engineers examining the aircraft immediately noticed the propeller. The blades were considerably wider than those found on previously captured Thunderbolts. The technical intelligence report detailed the new design but initially failed to grasp its profound significance, concluding that the modification likely improved takeoff performance rather than combat capability. This misunderstanding cost the Luftwaffe valuable time. Throughout February of 1944, more P-47 groups transitioned to paddle-bladed propellers. The 4th Fighter Group received theirs in early February. The 78th Fighter Group completed its transition by mid-February. By the end of the month, 6 of the 8 Thunderbolt groups in England were operating paddle-bladed aircraft. Each group immediately experienced a marked increase in combat effectiveness. German fighter losses climbed as Luftwaffe pilots discovered that their standard escape tactics were no longer viable. On February 21st, 1944, Jagdgeschwader 26 lost 7 Focke-Wulf 190s in a single engagement with the 56th Fighter Group. Unit Commander Major Klaus Mitos submitted an after-action report revealing his frustration. His pilots had engaged according to established doctrine, disengaging through climbing attacks when pressed. Every pilot who attempted this maneuver was shot down. Mitos requested immediate clarification on whether the Americans had introduced a new fighter type and whether existing tactical doctrine remained valid. Luftwaffe intelligence possessed no satisfactory answer. German comprehension gradually improved through observation and wreckage analysis. By March of 1944, Luftwaffe intelligence acknowledged that American engineers had modified the Thunderbolt's propeller to enhance thrust at low airspeeds, particularly during climbs. Reports circulated warning that American fighters could now contest vertical combat, recommending engagements only when possessing a clear energy advantage and disengaging through level, high-speed flight rather than climbing escapes. However, altering tactical doctrine across hundreds of fighter squadrons proved an insurmountable challenge. Pilots who had survived for the past year by climbing away could not instantly reprogram their ingrained survival instincts. The scale of this transformation became undeniable during Big Week. The massive bombing campaign targeting German aircraft production facilities, conducted from February 20th to 25th, saw the 8th Air Force launch over 3,800 bomber sorties, escorted by more than 3,600 fighter sorties. The vast majority of these American fighters were paddle-bladed equipped P-47s. The Luftwaffe launched over 2,000 sorties in defense. The Germans sustained approximately 355 fighter losses, with another 100 aircraft damaged beyond repair. American fighter losses totaled 28 aircraft. The exchange ratio had shifted dramatically. Thunderbolt pilots discovered that paddle-bladed propellers created opportunities extending beyond simple climb performance. Increased thrust at lower speeds improved acceleration out of dives, enabling Thunderbolts to build energy more rapidly after high-speed attacks. Pilots could execute dive and climb attacks repeatedly, maintaining the initiative throughout prolonged engagements. Improved thrust also enhanced turning performance at slower speeds. While Thunderbolts still could not outmaneuver Messerschmitt 19s or Focke-Wulf 190s in flat, horizontal turns, they could maintain sufficient energy in climbing turns to prevent German fighters from gaining an angular advantage. Major Francis Gabreski, commanding the 61st Fighter Squadron within the 56th Fighter Group, emerged as the leading proponent of what pilots termed the climbing spiral. Gabreski would engage a German fighter at co-altitude, typically around 24,000 feet. Rather than attempting to outturn the enemy horizontally, he would maintain speed and initiate a climbing turn. German pilots, observing the Thunderbolt's climb, would often follow, anticipating the American fighter's loss of energy and subsequent vulnerability. However, with paddle-bladed propellers, P-47s maintained their climb rate even while turning. Gabreski would spiral upward through 2 or 3 full circles, gradually depleting the German fighter's energy until the enemy stalled or was compelled to break off. At that critical moment, with the German fighter at low speed and high altitude, Gabreski would reverse his maneuver, dive onto the target, and open fire from a position from which the enemy had no escape route. Gabreski ultimately claimed 28 aerial victories flying P-47 Thunderbolts, making him the leading American ace in Europe, flying a single aircraft type. Nearly all of these victories were achieved after his squadron transitioned to paddle-bladed propellers. In post-war interviews, Gabreski consistently credited the new propeller as the single most crucial factor in the P-47's remarkable transformation. The modification necessitated minimal changes to pilot training. The aircraft simply performed as pilots desired, maintaining energy in situations where narrow-bladed equipped Thunderbolts would have faltered. The paddle blade program exemplified American industrial capability operating with remarkable efficiency. From initial concept to widespread deployment, the process required a mere 9 months. 2 companies designed, tested, and commenced manufacturing 2 distinct propeller configurations. Republic Aviation adapted production lines at 2 of its factories. The Army Air Forces developed new maintenance procedures, trained mechanics, and transported thousands of propellers across the Atlantic. No single element was revolutionary in itself. The achievement lay in the speed and scale of its implementation. The United States identified a critical deficiency and rectified it with greater alacrity than Germany could develop countermeasures. German aircraft designers possessed the technical knowledge to implement similar improvements. Both Messerschmitt and Focke-Wulf employed experienced propeller engineers who understood the theoretical advantages of increased blade area. However, Germany's wartime economy in 1944 could not support rapid modification programs. German aircraft production operated at maximum capacity, focused on producing existing designs in sufficient quantities to compensate for combat losses. Introducing new propeller designs would have necessitated retooling production lines, recertifying aircraft performance, updating maintenance manuals, and retraining mechanics. Production disruptions would have resulted in the loss of thousands of fighters at a time when Germany desperately needed every available aircraft. The Germans were trapped by their strategic circumstances. They needed to match American advancements, but could not afford the production disruption required. This highlighted fundamental divergences in the American and German approaches to aircraft development. American designers embraced solutions that were good enough and could be implemented rapidly. The paddle-bladed propeller was aerodynamically less efficient than more sophisticated designs. It generated more drag than narrower. It was heavier, requiring reinforced hubs and pitch control mechanisms, but it effectively solved the immediate problem without requiring years of development to optimize every parameter. German designers often pursued theoretical perfection at the expense of practical implementation. German propeller designers worked on advanced variable pitch systems that theoretically outperformed the rudimentary American paddle blades, but these advanced designs existed primarily on paper, never reaching operational service in significant numbers. By March of 1944, the paddle-bladed Thunderbolt had become the standard American escort fighter in Europe. The aircraft was no longer a compromised platform, awaiting replacement by the longer-ranged P-51 Mustangs. The Thunderbolt had evolved into a formidable air superiority fighter, outclassing German opponents in most combat scenarios. The psychological impact was substantial. American bomber crews, who had watched helplessly as German fighters climbed away throughout 1943, now witnessed enemy fighters being pursued and destroyed in climbing combat. German pilots, already demoralized by the increasing numerical superiority of American forces, faced a tactical environment where their advantages had been nullified. The Focke-Wulf 190, designed to be superior to the Thunderbolt in nearly every performance category, found itself matched or exceeded in the one area where it had maintained a clear advantage. The Messerschmitt 109 could no longer rely on vertical maneuvers to escape combat. German fighter losses climbed steadily throughout the spring of 1944. Many veteran pilots who had survived years of combat were shot down by Thunderbolts they believed they had successfully evaded. The full impact became evident during the preparations for D-Day. Throughout May of 1944, American fighters conducted intensive operations aimed at achieving air superiority over France. Thunderbolts ranged across northern France, attacking German airfields, destroying aircraft on the ground, and engaging any Luftwaffe fighters that attempted to interfere. Paddle-bladed equipped P-47s proved especially effective in these fighter sweeps. When German fighters scrambled to intercept, they typically climbed from lower altitudes to reach American fighters operating at 20,000 to 25,000 feet. Thunderbolts could now dive on these climbing German fighters, attack, and then climb away before the Germans could retaliate. On June 6, 1944, as Allied forces stormed the beaches of Normandy, Thunderbolts provided air cover throughout the day. German fighters that attempted to attack the invasion fleet or support German ground forces were consistently intercepted and destroyed by paddle-bladed equipped P-47s. The Luftwaffe managed fewer than 100 sorties over the invasion beaches during the critical first 24 hours. American fighters flew more than 8,700 sorties during the same period. This overwhelming superiority was achievable because American fighters achieved kill ratios of 4-to-1 or better. The paddle-bladed propeller, by eliminating the Thunderbolt's primary weakness, contributed directly to achieving the air superiority that made the invasion possible. Statistical data validated the experiences of aviators. During the initial 3 months of 1944, prior to the widespread adoption of paddle-blade propellers, American fighter aircraft in Europe achieved an aggregate aerial victory ratio of approximately 1.8-to-1 against their German counterparts. By the second quarter of 1944, with the majority of American fighters outfitted with these enhanced propellers, the kill ratio surged to 3.2-to-1. This upward trend continued into the third quarter, reaching an impressive 4.6-to-1. While these advancements were not solely attributable to the propeller modifications, as factors such as growing American numerical superiority, improved pilot training, and Germany's deployment of less experienced pilots to offset mounting casualties also played a role. Combat reports unequivocally highlight the significant contribution of enhanced climbing capabilities to these victories. The Curtiss Electric C542S paddle blade propeller, a widely adopted variant, featured 4 blades with a 13-foot diameter. Each blade possessed a substantially larger surface area compared to its narrower predecessors, translating into dramatically improved thrust at reduced air speeds. The Hamilton Standard Hydromill paddle blade, incorporated into later production P-47s, offered comparable performance with added operational advantages. Its hydraulic pitch control system was simpler and more dependable than the Curtiss electric mechanism. The overall blade area was nearly identical, and the combat effectiveness was virtually indistinguishable. The manufacturing endeavor required to outfit the entire P-47 fleet showcased the immense scale of American industrial output. Between June of 1943 and December of 1944, both Curtiss-Wright and Hamilton Standard produced thousands of propeller assemblies, each comprising 4 blades, a hub assembly, a pitch control apparatus, and mounting hardware. The blades were forged from an aluminum alloy, precisely shaped through machining to achieve optimal airfoil characteristics, and subjected to heat treatment for maximum structural integrity. Each individual blade demanded approximately 14 hours of machining time, not including the preparatory and finishing stages for the raw materials. Distributing these propellers to operational units stationed in England presented considerable logistical hurdles. Each complete assembly weighed around 650 pounds and necessitated careful handling to prevent damage during transit. Propellers were encased in sturdy wooden crates with protective internal bracing and transported across the Atlantic via cargo vessels, with voyages typically lasting 2 weeks. Upon arrival, the propellers were conveyed to air depot facilities for installation by mechanics. The process of replacing existing propellers, fitting the new ones, adjusting the pitch control systems, and conducting ground tests typically required about 16 hours per aircraft. Between January and June of 1944, air depot mechanics in England retrofitted over 1,000 Thunderbolts while simultaneously ensuring the operational readiness of frontline fighter groups. The tactical evolution of operations involving paddle blade-equipped Thunderbolts continued through the summer and autumn of 1944. Aviators developed increasingly sophisticated strategies to leverage the improved climbing performance. One particularly successful maneuver, known as the vertical scissors, involved 2 Thunderbolts engaging a German fighter in an upward spiraling dogfight. As the enemy aircraft ascended to evade the first P-47, the second would position itself to attack once the German fighter depleted its energy and its ability to climb effectively diminished. The German pilot faced an untenable choice: continue climbing until stalling, rendering him an easy target for the pursuing Thunderbolt, or roll out to maintain airspeed, allowing the lead Thunderbolt to execute a diving assault. Another significant development was the utilization of paddle blade Thunderbolts for low-altitude ground attack missions. The enhanced low-speed thrust enabled heavily laden P-47s to sustain speed and maneuverability even when carrying substantial payloads of bombs or rockets, totaling up to 2,500 pounds. Pilots targeting German ground installations could initiate attack dives from lower altitudes, thereby reducing their exposure to anti-aircraft fire. Following the release of their ordnance, paddle blade-equipped Thunderbolts could ascend away from their targets more rapidly, further mitigating their vulnerability. Between April and September of 1944, Thunderbolts executed over 88,000 ground attack sorties, incurring approximately 820 losses from all causes, a loss rate of under 1%. The inherent versatility of paddle blade Thunderbolts allowed them to remain integral to frontline combat operations even as the longer-ranged P-51 Mustangs became available. Numerous fighter groups opted to retain the Thunderbolts specifically because their enhanced performance made them exceptionally adept in a variety of roles. The 56th Fighter Group, commanded initially by Colonel Hubert Zanker and subsequently by Colonel David Schilling, exclusively operated Thunderbolts throughout the entirety of the war. Despite opportunities to transition to Mustangs, the group's pilots maintained that the aircraft's robust construction, its 8-gun armament, combined with the superior climbing performance afforded by the paddle blade propellers, rendered it preferable to the Mustang for their operational needs. German fighter pilots who survived the conflict consistently identified the paddle blade Thunderbolt as one of the most formidable American adversaries they encountered. Major Gunther Rahl, who amassed 275 victories, stated in post-war interviews that the improved Thunderbolts posed a significantly greater threat than their earlier iterations. Rahl indicated that German aviators were compelled to afford paddle blade Thunderbolts the same level of respect previously reserved for P-51 Mustangs, recognizing that the American aircraft could rival German performance across most engagement scenarios. The engineering insights gleaned from this program profoundly influenced subsequent American aircraft development for the remainder of the war. The swift development and deployment demonstrated that incremental enhancements to existing airframes could often yield superior value compared to the creation of entirely new aircraft designs. The P-47 itself benefited from ongoing improvements beyond propeller modifications. Water methanol injection systems boosted engine power to between 2,500 and 35 horsepower for brief durations. When coupled with the improved thrust characteristics of the paddle blade propellers, this further amplified performance. The P-47M, introduced in late 1944, incorporated both of these advancements and possessed the capability for rapid ascent, matching or surpassing the climbing performance of any German fighter. The financial outlay required for the development and implementation of paddle blade propellers was modest when contrasted with the operational advantages achieved. The research and development expenses for both the Curtiss and Hamilton standard propellers, encompassing wind tunnel testing, prototype construction, and flight evaluations, aggregated approximately $3 million. In comparison, developing a completely new fighter aircraft would have entailed an expenditure of at least $100 million and a time frame of 2 to 3 years before reaching operational deployment. The paddle blade propeller epitomized the kind of cost-effective improvement that rendered American air power exceedingly difficult to counter. Furthermore, paddle blade propellers underscored the critical importance of feedback mechanisms linking combat operations with aircraft design. Deficiencies in narrow blade propellers were identified by frontline pilots who submitted after-action reports detailing instances of German fighters evading engagements through climbing maneuvers. These reports, channeled through intelligence networks, reached engineers who could ascertain the root causes and devise effective solutions. This feedback loop operated with remarkable celerity, with combat-identified issues leading to engineering resolutions within months. German forces possessed analogous theoretical feedback systems. However, these were increasingly hampered by the pervasive chaos stemming from Germany's deteriorating strategic situation. The strategic implications extended beyond direct aerial confrontations. The attainment of air superiority over Europe, to which the improved Thunderbolts significantly contributed, enabled Allied ground forces to advance with minimal impediment from German air power. During the Normandy breakout in August of 1944, American ground units advanced under the protective shield of air superiority, largely maintained by Thunderbolts. German ground formations attempting to withdraw or redeploy found themselves under relentless assault from Allied fighter aircraft. The enhanced climbing capability meant that any German fighters attempting to interfere with ground attack missions could be swiftly intercepted and neutralized by escorting P-47s. The last major aerial engagement involving a substantial number of paddle blade Thunderbolts occurred during the Battle of the Bulge in December of 1944 and January of 1945. When German ground forces initiated a surprise offensive through the Ardennes, adverse weather conditions initially precluded effective aerial operations. Upon the dissipation of the bad weather on the 23rd of December, Allied air forces unleashed massive assaults against German ground formations and their supply lines. Paddle blade-equipped Thunderbolts conducted hundreds of sorties daily, targeting German armored vehicles, trucks, and artillery positions. Luftwaffe fighters attempted to intervene, but were consistently repelled by the escorting P-47s. By February of 1945, organized Luftwaffe resistance across Western Europe had effectively collapsed. German fighter units were redeployed to defend the homeland against an escalating strategic bombing campaign. Paddle-blade Thunderbolts had played a pivotal role in achieving this air dominance, although their contribution was often overshadowed by the more celebrated reputation of the P-51 Mustangs. Military historians examining the air war have at times understated the significance of the Thunderbolt, noting that the P-51s achieved a greater number of aerial victories and penetrated deeper into German territory. However, this perspective overlooks the crucial fact that the Thunderbolt's transformation, driven by paddle-blade propeller modification, occurred at a critical juncture when German fighter forces still posed a substantial threat. Between January and December of 1944, Thunderbolts were credited with destroying 3,802 German aircraft in aerial combat, while losing 824 P-47s to all causes within the European theater, resulting in an overall kill ratio of 3.7 to 1, comparable to or exceeding that of other American fighter types during the same period. More importantly, the Thunderbolt's evolution from a mediocre climber to a capable vertical fighter occurred during a period when such an ability was most critically needed. The post-war disposition of paddle-blade Thunderbolts illustrates the rapid obsolescence of wartime innovations. As jet fighters entered service, propeller-driven P-47s quickly became antiquated. The majority of surviving Thunderbolts were either dismantled or sold to foreign air forces. The technical advancements that rendered paddle-blade Thunderbolts effective combat aircraft were eclipsed by the revolutionary capabilities of jet propulsion. Few of the pilots who flew the improved Thunderbolts in combat ascended to positions where they could ensure that the propeller modification received its due historical recognition. Nevertheless, paddle-blade propellers represent a fundamentally important category of military innovation that warrants greater acknowledgement. It was not a revolutionary breakthrough that fundamentally altered the nature of aerial combat. Rather, it was an evolutionary enhancement that refined an existing platform by rectifying its most critical deficiency through relatively straightforward engineering. This type of innovation, less dramatic than revolutionary new technologies, but often more immediately impactful, characterized much of America's military success during World War II. The capacity to identify problems, devise practical solutions, implement them swiftly, and deploy them at scale conferred decisive advantages upon American forces. The engineering principles underpinning paddle-blade propellers remain pertinent to modern military aviation, notwithstanding the transition to jet propulsion. The fundamental tenet that blade area must be optimized for specific operating conditions rather than pursuing theoretical maximum efficiency is applicable to the design of turbine blades, helicopter rotors, and propulsion systems for unmanned aerial vehicles. Military engineers continue to grapple with the challenge of balancing multiple performance requirements across diverse flight regimes. The German perspective on paddle-blade Thunderbolts offers sobering lessons regarding the repercussions of industrial and strategic deficiencies. German engineers possessed an understanding of propeller theory comparable to their American counterparts. German aircraft manufacturing facilities were capable of producing improved propellers had they been provided with the necessary resources and opportunities. However, Germany's deteriorating strategic position, resource scarcity, and increasingly compromised industrial infrastructure rendered ambitious improvement programs unfeasible. The success of paddle-blade Thunderbolts was not a consequence of superior American engineering skills, but rather of an American industrial capacity that could sustain rapid innovation, a feat that German industry could not replicate. Wars are not won by singular wonder weapons, brilliant strategies, or revolutionary technologies. They are secured through the cumulative impact of thousands of incremental improvements, each addressing specific challenges, each implemented efficiently, and each contributing to overarching superiority. The paddle-blade propeller represented one such improvement among many. But its advent occurred at a crucial moment when German forces were still capable of contesting Allied air supremacy. By eliminating the Thunderbolt's primary vulnerability, the modification was instrumental in establishing the air dominance that facilitated the invasion of Europe and hastened Germany's defeat. This achievement, originating from the diligent work of propeller engineers rather than the celebrated exploits of fighter pilots, deserves recognition as one of the decisive technological contributions to the Allied victory in Europe.